In order to create this apparatus, we decided to make 11 bobs. So each bob consists of a wood ball connected to a piece of string. Each string differs in length. The first one is 24 centimeters. The last one is 34.4 centimeters long. The bobs in the middle have a decreasing length so that it looks like they're all increasingly short or increasingly longer. Each bob is then 3 inches apart from one another. Explain what the pendulum bobs are doing when your apparatus exhibits wave motion.
So, the pendulum bobs in this apparatus exhibit simple harmonic motion. What is simple harmonic motion? Simple harmonic motion is the repetitive motion around a fixed point. So before the apparatus starts, as you can see, the bobs are just lying still in the center. So this is the equilibrium position. When we start the apparatus by pulling back the bobs, they swing back and forth around the equilibrium position. So this is simple harmonic motions, and they swing back and forth around the equilibrium position. Gravity and the tension of the string both act as restoring forces here. The restoring force is proportional to the displacement of the pendulum when the angle is relatively small, or less than 15 degrees. The magnitude of the restoring force decreases as the bob moves towards the equilibrium position. Since the angle is so small, the displacement is still proportional to the restoring force.
Determine 3 amplitudes for which the apparatus produces nice smooth waves. What are these 3 amplitudes? Explain how you decided on them and how you measured each amplitude.
So the 3 amplitudes we used were 22.56 centimeters, 15.61 centimeters, and 9.12 centimeters. And we found this by first finding the maximum or the largest amplitude from our equilibrium position. So we measured from the equilibrium position back, and that happened to be 22.56 centimeters. And then we did the same for the shortest amplitude. We just measured from the equilibrium position to where we want the shortest one to be, and that happened to be 9.12 centimeters. And then for the middle amplitude, we just found a distance that was kind of in the middle of 22.56 and 9.12.
Use the middle amplitude as your baseline. Describe what happens to the frequency of the waves if the waves have a bigger amplitude than the baseline amplitude. Include an explanation of your observations regarding the frequency when the amplitude is increased.
Okay, so this is our baseline amplitude, which is approximately 15.61 centimeters. You can see the waves here. And then when we pull it back more and increase the amplitude, so this is approximately 22.56 centimeters. And so because the amplitude has increased, the frequency has decreased because there are less waves per second in our pendulum. Because each bob has more of a distance to travel, the frequency decreases.
Describe what happens to the wavelength of the waves if the waves have a smaller amplitude than the baseline amplitude. Include an explanation of your observations regarding wavelength when the amplitude is decreased.
Okay, so this is our baseline wavelength, which is approximately 15.61 centimeters. And then this is our smaller wave amplitude, which is approximately 9.12 centimeters. So as you can see here, the wavelength from our baseline amplitude is bigger than our wavelength from the smaller amplitude. And this is because each individual bob has more oscillations, and that creates more individual waves in between. So that's how you can see the wavelength is decreasing, because there are more waves.
Calculate the velocity of the wave for the first few waves created by the apparatus. Include a data table showing the measurements you took in order to calculate the velocity. Describe in words how you measured the frequency and wavelength.
Okay, so we know that velocity is the product of wavelength times frequency, where wavelength is represented by lambda and f is represented by frequency. So because we know this, in order to calculate velocity, we must know the wavelength and the frequency. So in order to find the wavelength, we let our apparatus create waves, and so we let the pendulums go to simple harmonic motion. And while we did that, we had a ruler under the apparatus where one person actually took pictures of the apparatus while it was in motion, and later we looked back at those pictures and we could see the wavelength. For frequency, one of us timed while the other counted the number of waves, and so each time we counted a wave, we would stop the stopwatch. This actually finds the period, but period and frequency are inversely related. So if you know period, you can easily figure out frequency by doing 1 over period, or 1 over seconds per wave.
You can physically change something about your apparatus that would affect the velocity of the waves. What physical aspect in your apparatus can you modify or change that would change the velocity of the wave you calculated in number 3? Include an explanation why making these changes would affect the wave velocity.
So one physical aspect that we would change would be changing the length of the strings that the bobs are connected to themselves. So as you can see, this formula shows how to find the period of a pendulum, where t equals 2 pi times the square root of L over g. L is the length of the string, and g is the free fall acceleration. So as you can see, you could change L, and that would eventually change the period. Period is also inversely related to frequency, so then that would change the frequency if you change the period. And to find velocity, it's the wavelength times the frequency. So changing the frequency would end up changing the velocity. So in the end, changing the length of the strings would end up changing the velocity.
In order to complete this project, we had to use many sources. Before we started this project, many of us didn't even know what a pendulum wave actually was. There were many great resources available online for this project, and they all helped in some way. The works cited helped our group decide on measurements, see what the final product should actually look like, and understand the physics behind the final project. First, the sources helped us start thinking about the project. After we watched the bowling video, we knew the basics of what it should look like. However, we obviously didn't have bowling balls or the resources to create a pendulum wave that large. So in order to find simpler ways to create this project, we used online sources. Crockett's experiment had many great instructions of how to actually build the apparatus. Additionally, one website showed us household objects that could have been used for the pendulums, such as batteries, screws, or keys. Later on, though, we decided not to use household objects. However, all of the sources said about the same thing. They said that the bobs should all be heavy enough so that there wasn't considerable air resistance. So in that way, the sources definitely helped us start thinking about the final project. They also showed us, got us to start thinking about the lengths and the measurements. So we wanted the lengths to be consistent, so we decided on wooden balls that we purchased. The source was still really good though, because it showed us that the type of bob didn't really matter as long as the weight was consistent and the length was consistent.
One of the biggest challenges we had were deciding on the measurements of the pendulum strings. So the first time we did this project, we used shoestrings instead of these strings over here. but these did not work very well. The string's lengths were not very exact, so when the pendulum did a wave, it didn't work very well. And in order for the pendulums to move as a wave, the string lengths need to be exactly precise. And all the sources told us this, so we decided to remake the project. However, at this point, we were unsure of what lengths to actually use. We knew we wanted the apparatus to have at least 10 pendulums, and that they should each be about 8 centimeters apart, which they are. Using your sources, we decided on precise lengths for the pendulum strings. The longest string was 34.4 centimeters down there, and the shortest string was 24 centimeters, this one.
Lastly, the sources helped with the math behind the final product. We were very unsure of how to actually find the frequency. However, many of the sources showed good ways to use a stopwatch and have accurate data. Also, explaining why the pendulums were in simple harmonic motion was a bit challenging. Sources like 1 and 2 helped explain some of the math. We were also a bit confused about the amplitude. After a lot of reading, we realized that we could easily find the amplitude by finding the displacement distance from the equilibrium position. The sources were very helpful because they seemed like they were written by actual physics majors or teachers. They were also easy to follow even though some complicated math was involved.
The violin is producing sound waves. Sound waves are an example of mechanical waves because they require a medium to travel through. The medium is the air, and sound waves cannot travel through a vacuum. Here, the ripple in the water is an example of a mechanical wave. The ripple contains both transverse and longitudinal waves. The medium that the wave is traveling through is the water.